Good morning, good evening, good afternoon, wherever you are on this planet, and welcome to our SETI Live. My name is Franck Marchis, and sorry, I have an issue with my audio right now. I hear myself. Good. Here we are. Yes. So, my name is Franck Marchis. I'm a senior researcher at the SETI Institute, director of citizen science at SETI and Unistellar. And today we are going to talk about a topic which is, I think, fascinating, interesting, and everybody's talking about it. We're going to talk about AI and how AI can help in planetary science. So, for this, I invited two renowned scientists who have been working in this field. First, let me introduce you, Adam Lesnikowski. Hi, Adam. How are you?
Well, how are you?
So, Adam, you are a doctorate candidate in the logic group at UC Berkeley. Is that correct?
That's correct.
And you are calling us from UC Berkeley right now?
That's right. Berkeley, California.
Berkeley, California. And on the other screen, we have Daniel Angerhausen. Hey, Daniel, how are you?
Yes, hi Frank, hi everyone. Good to be back with this project today.
So Daniel is an astrophysicist, astrobiologist, and he has expertise in planetary science and AI. And so today we are not going to talk about everything about planetary science and AI. We are going to focus on the recent research you published in February of last year, based on how machine learning can help us uncover anomalies on the moon. So since we're going to talk about the moon and anomalies, my first questions, and I think that's why we have a lot of people watching us right now, is what is you think the wildest thing that AI will find on the moon in the future?
That it will find or that I wish it would find.
Well, you can say so the way you want to this question. So go ahead, Daniel.
So I think, I mean, that's why we started this and why we got this idea when we met the first time at the SETI Institute and talked about this was really to see if we might actually find some crashed alien probes or the entrance to some ancient bases below the lunar surface. But I'd also be happy if we find a $1 trillion rock of lithium or something else that might be interesting for us, a good landing site to build a hotel. So there might be many more things besides crashed UFOs that we might find with our algorithm.
And what about you, Adam?
Yeah, it's a great question. I would say there's a whole bunch of things. There's like sort of solar, rather probes that may have landed from past missions from both the Soviets and the U.S. that maybe weren't as well documented. Obviously, the things that Daniel talked about, and I guess all the kind of crazy geological things that we sort of outline in the paper, things like lunar cave skylights and irregular Mare patches and things that people in planetary science care about. So it's a bit of a fishing expedition. I don't really want to say that we want to find anything in particular. We kind of want to let the data speak for itself and see what's out there.
Okay. All right. Well, let's talk about this work. I mean, it's so you. Let's just set the stage first. Daniel, what is the Lunar Reconnaissance Orbiter and why you use this?
Yes, so the Lunar Reconnaissance Orbiter is kind of like our workhorse when it comes to data from the moon. So it's a satellite launched in 2009 with a bunch of instruments covering almost the whole electromagnetic spectrum. And this is really designed for prospecting of the moon, for exploring the moon, for future landing sites. They have altimeters on board to get the altitude. There's really a lot of instruments on there that give us a great picture of what's going on the moon and where we might eventually going.
And it's a mission which is still in activity?
Yeah, it's still live and well, standing data every day. So it's
impressive. 2009. Yeah. All right. So Adam, so this is kind of been the source of the work you've been doing. So tell us a bit about the data. What data did you use specifically? How much data are we talking about here?
Yeah, good question. So it's all image data, so satellite surface imagery data of the moon in this particular case, and it's basically black and white grayscale images, and there's a lot of it. So we sort of have scaled up how much we train and inference on and test on. But the whole big pile, it keeps growing. But it's, I believe right now, when we talk to our co-author, Valentin Bickel, who's the data expert, he sort of estimates it on the order of petabytes now from this particular mission. So we're talking about, if you have a laptop with, let's say, I don't know, a terabyte of data, it'd be like 1,000 laptops. So we're talking like, data center scale data sets that we have.
All right. So it's not possible to analyze this by hand, like we used to do in my time, basically.
By hand, if you're patient, yes, you could do it. So, so for our method, we look at these like 64 by 64 pixel square patches. Just one covering of the moon, we estimated at one point it's like 10 to the 10 many patches. So that's like 10 billion. If you take like a second to do that, I think you'd be like in the hundreds of years. So,
okay.
Life extensions around the corner. Possibly.
If you don't do anything else, don't sleeping, and just one person could do it, but it will take 100 years.
Would be.
We're not patient.
Infeasible, exactly, by one person or even a group of people.
But talking about person, we have people watching us and listening to us from various places around the world: Scotland, Coquimbo in Chile, in northern Germany, Tampa, USA, Brazil, New York, Macau and Maui, Wales, UK, and welcome. So we are talking about how we can look for lunar anomalies using AI. And for this, we are going to dig into the algorithm. So Adam, I'm going to ask you to explain to us how the AI system work without any slide and without using any word that none of us will understand.
All right. Yeah, let's give it a go. I guess first hi to everyone from all those places. It's great to see all the interest and people from around the world interested in this. So I guess I would maybe compare it to I had a chance to play a game of code words at a party, like maybe some weeks ago. And code words is this game. It's like a party game where you have teams, and one part of the team basically they have a secret word that they want to transmit to the receiving part of the team, and the sending part of the team has to say some particular word, let's say skyscraper, but they can't actually use that word. They have to use other words, and it's limited how many words they can use. So they can say like building, tall, city, and the receiving team has to guess this. So that's kind of the essence of what we're doing. We have kind of a train process where the machine learning algorithm, which has this both sending and receiving guessing parts of the network. And during the training process, we show it lots of images, so like tens of millions of images. And the receiving team, part of the network, has to recreate the image. So that's usually not hard, but the trick is that in the middle of the network, there's this like informational bottleneck where it's only kind of these small code words that can be transmitted. And so the trick is how to most efficiently say those things. So say like you have some image of a crater on the moon. Intuitively, the network, the part that's sending it, can say things like crater, small, upper right, in like the lowlands of the moon. And then the decoder has to do something to recreate it. And it's judging how well it recreates it. And so our method basically takes one of these networks that's trained in this way. And then for all the images that we care about, it tries to recreate the images that we have it to test. And so for like regular boring images, so things that you normally see on the moon, it does a pretty good job. But the trick or the kind of insight, and this isn't really our insight, it's just the insight of the anomaly detection community, is that things that are sort of normal or typical, they're going to be recreated pretty well, because in this training process, it's seen a lot of these, it's had a lot of practice. But for things which are unusual, like these volcanic pits or fresh impact craters or potentially other things, landed assets like Surveyor 3 or Apollo, whatever, 1711, it's going to do really poorly just because it hasn't seen many of those. So think like in your team, in your CodeWords team, you've done a lot of things with buildings and foods, and then all of a sudden I ask you to transmit a jellyfish. you're probably going to do pretty poorly. So
Mhm.
that's kind of the insight into the method.
Okay. So this is an approach which is kind of very different to what we used to do traditionally to analyze planetary image of terrestrial planet. Daniel, how we used to, can you tell us about why this method is different to the previous one we used in the past?
I mean, first of all, just the fact that we're using machine learning or automatic techniques. So the paper we actually based our research on, they literally tried, had a couple of grad students looking through images. So that's the first thing, just to use an automatic method on its own. And then what I think makes our method unique or different from other approaches is that our method is an unsupervised method. So often people use supervised methods, so look for images that have squares or triangles or circles, but then you introduce a lot of biases. Then it sees, you know, cats and dogs everywhere and circles and triangles anywhere. And ours is a really unsupervised and therefore unbiased method. So it's really a very, very agnostic search for outliers. So there's no human bias in the loop. It's really what the computer thinks looks different than the rest on the moon. So this really takes kind of like this human bias completely out of the loop. And I think that what makes this method very unique and also applicable to a lot of other cases, actually, which we might talk a bit later about again.
Yeah. Okay. Well, we have people joining us from the Nordics. I'm assuming it's somewhere in Scandinavia, from the Bayou in Louisiana. Hello, Ron, and Germany, and welcome. So let's go back to the result then. So you have been running this. I have a very naive question. How long does it take to analyze all the REO data using your algorithm?
Yeah, so it's a great question. So for any particular image, and you can actually, we call it batch them. So like we put them in kind of a batch of a lot of images, and just the way the hardware is set up, GPU and kind of parallel inference, it could do it quite quickly. So for like, on average, I think it's right now on the order of 100 milliseconds per an image. We could probably get it down another factor of 10 using probably the latest hardware. So we ran these experiments now maybe a couple years ago, probably 2023-ish range. So I'm guessing just in terms of, you would think probably order of magnitude, probably 10 milliseconds. So that's like one 1/100th of a second for a single image.
Mm-hmm.
And the nice part about it is that it can be sent to many different computers at once. So that's for one GPU. But if you have the budget for, say, 1,000 GPUs, you can send one image to the first GPU and second image to the second GPU, and it's extremely parallelizable. So basically, your budget's the limit in terms of how fast you want to have it done. And we actually had one instance where we tried to have it run on 100 GPUs just to speed things up, which was a bit of engineering challenge, but it's certainly feasible to do. It's one of the, I guess, embarrassing.
So it doesn't take 100 years.
No. So
it's way less.
It's way less.
Okay. All right. So people are all waiting. I see that people are commenting. So what did you discover? What kind of anomaly this AI has detected?
Yeah, so I guess the biggest ones from the paper, the things that have the biggest signal, one are these volcanic pits. So I'm not really like the geologist here, but I'll try to speak for Valentin based on what we talked about. So I guess there's these like lunar tunnels on the moon, and sometimes those horizontal tunnels, the roof will collapse, and these leaves these very kind of stereotypical on images skylights. And the reason they're important is that I guess people who want to habitate the moon and eventually set up some colonies, they think these are probably some of the best natural settlements for initial humans. So there's probably some hundreds of them that have been found, and you can find them they really have like a strong signal with our method. Another one is fresh impact craters, and that's like useful for kind of measuring weathering patterns on the moon and how fast like meteors and micrometeors hit the moon. And then kind of a moderate signal are these landed assets. So we looked at some of the Apollo landing sites and also Surveyor 3, which is kind of in the Apollo area. but basically technosignatures, but ones that we as humans have put up there. And kind of the reason why we think this works is that these things are fairly rare, both the skylights, fresh impact craters, and then these landed assets are pretty regular visually, but also for these models when you run this method on them. So those are probably the three biggest classes. And then there's a fourth one, which are these irregular mare patches, which I guess are a bit of a puzzle for geologists, as far as I understand.
Okay. Daniel, can we talk about the Apollo sites? Because I know a lot of people want to hear about that. So this method detected them, all of them? You detected what exactly? What's the signature that was detected by this AI?
So as Adam already explained, we get what the experts call reconstruction loss. So this anomaly value. So we put an image in and we get and the algorithm gives it a number. 5 is low anomaly and 150 is a high anomaly. And all these little patches that included Apollo landing sites got really high numbers. So we get a distribution with a huge peak, which are the normal, and then you have a long tail, and all these Apollo images are in the tail. So this is how they separate from the average image, and this is how we could separate them from just normal images. So we detected technosignatures on the moon, just that these technosignatures are human so far.
A human signature.
And this was actually where we were coming from, right? So we knew we have this kind of ground truth data in a sense on the moon because we planted these Apollo landing sites there. So if we find them, then the question is, what else can we find? And that also means that once we find nothing, we can kind of like exclude anything that is on the size order, or similar to the Apollo landing site. So this is kind of like the advantage we wanted to leverage, that we have this ground truth data set planted there. Yeah.
Have you seen any things that you didn't expect? I mean, without talking about aliens, like for instance, any crash of satellites or anything that ad posteriori you could explain?
So I think we tried some of these recent missions. I think the Vikram or Bereshit impacts, we were able to find them. I have to say that we haven't, and this is where you mentioned the word budget. We are still kind of like looking for the budget and the human power to really do the whole lunar surface. So we should mention that what we analyzed so far was really just a small fraction of the lunar surface. So essentially we have the pipeline there, we have the code there, but to scale this up to the whole lunar surface, we need also not a lot of money, but a bit of money and also time to have this analyze the whole lunar surface. But what was already surprising is that we got all these other geological features, and from these tests that we did, we are pretty convinced that if there's anything else technologically or in the scale of fresh impacts or things like that, crashed landers or crashed stages, where we would find them.
Yeah. Oh, yeah. That's interesting. We're gonna go back to this. What will be the next step? Okay, so we're gonna take questions in a few minutes, for people who wants to ask. But let's talk about a bit the next step. So, Daniel, we're using this technology on the moon.
Mm-hmm.
Is that something that we could consider using for other planets? And which one?
Yeah, for sure. So as if we have data of the same quality, so we are already thinking about expanding it to Mars, which has a really nice camera, which also gives us high resolution data. So that's probably also something we should mention, that LRO data, 1 pixel is between 30 and 50 centimeters. So this is also why we can look for anomalies of that size. If you have, images of, let's say, Mercury or Ceres, which have a pixel of a couple 100 meters, then of course you can only search for anomalies that have this size. But if there's a kilometer size anomaly on Ceres, we should be able to get this also from Ceres surface imagery, for example. So in principle, you could expand this this algorithm to any other body in the solar system where we got surface imagery. And then in principle, these unsupervised anomaly detection algorithms could be applied to any other data set. So I know, for example, people are using it for Kepler and TESS light curves, and probably also going to use it for LSST data to really just find needles in haystacks, which is probably the classical SETI experiment, if you want so, right?
Okay, so there is some challenges, of course. When you use an algorithm like this, Adam, maybe you want to answer to that. You can expect that you need to have some specific type of data or specific amount. If I come with you to see you and I say, have 20 images taken with a telescope of an asteroid, can you run your algorithm? What you're going to tell me is no, right? Because not enough. So give us a bit like what is needed in terms of the quality of data or in terms of the quantity as well to make this valuable.
Yeah, so what we did was we trained on 50 million images. So that's definitely a lot more than the 10 or 20 you mentioned. I mean, one potential approach, people do this a lot in machine learning AI, is they'll train on a lot of general data, so it's like pre-training paradigm, and then they'll fine tune on a smaller number of examples. And in vision, maybe all depends on kind of the applications and domain and what kind of models you have, but maybe like a couple hundred will work for if you have like a pretty high quality pre-trained model to fine tune on those. So maybe it'll work. We didn't really explore it in this work. We just kind of directly trained on kind of the tens of millions of lunar images. And I guess you also mentioned maybe challenges or biases, Frank, is that right? In terms of, yeah, so I guess the biases, it's a big question, I guess, in machine learning, where kind of now there's a lot of attention focused on what kind of biases these large language models may have and how they're different as intelligences versus human intelligences. For image models, for instance, I'll just give you one example. So-called bias, you could say, in these vision models is that they're open to these adversarial examples, or they're prone to these adversarial examples where imperceptible changes, at least human imperceptible changes to images, will lead to misclassifications or all other kinds of pathologies in the machine context. So I guess I would say, just zooming out 30,000 feet, is that it's kind of complementary to humans. There's a lot of things that have been done, at least as far as I understand in SETI, in terms of trying to find these features using human crafted ingenuity and engineering. For machines, maybe they have their own biases, but kind of the idea is that it's a different set of biases. So like, you have the Swiss cheese model of safety or reliability, where maybe there's like one hole as you're going through. So like maybe stuff falls through because like we as humans have certain biases, but the biases of machines may line up in a different region, so that on the whole we're able to catch stuff and cast a broad net in terms of kind of accelerating scientific discovery. So I don't really have much to say in terms of like, here's the answer of biases for these models. I guess my intuition, just experience, is that the biases may be somewhat different than humans, and hopefully that diversity of biases will lead to a system that is more robust and has better kind of recall than just humans by themselves. At least that's the vision.
Okay, thank you. Something I'm surprised, why don't we implement this algorithm directly into LRO? So we have right away, when the system is taking an observation, a detection of something, an anomaly. Is that something that you could do?
I think there's
no
certain.
reason.
Go ahead.
Yeah, there's no reason not to. I think, it's just a matter of building it and running it. Now that we have the trained model, and actually the weights, the code, and the data set labels are all publicly available. So we wanted to make those public just to kind of have some reproducibility that's easy for other people building on top of this work. So there's no reason in principle not to, other than just engineering and computer time costs to do it. And I guess maybe it's not like, well, I'll leave it up to the planetary scientists to decide how useful this might be. But technically, there's no reason why you couldn't have this.
Daniel?
Some spacecraft actually do this already on board, especially if the downstream rate, for example, is low and you have to on board decide which data to send, which data not to send. There's already machine learning deployed to, for example, if you do Earth observations, to filter out stuff that has only clouds on it and things like that. Then there's other, like everything that has to trigger alarm, like if you do, let's say, gravitational wave observations or gravitational microlensing observations, you get an alarm if something does an outlier, right? So these things exist already, especially if you need to make real-time decisions to follow up something. So I think in these cases especially, it's going to be interesting, and this is why it might actually be super important to apply these for, let's say, LSST. So if you do these all sky photometric surveys, then it's probably great to identify these anomalies already while they're happening, that you can really focus all other telescopes on that anomaly. Yeah.
Right. I'm gonna take some question briefly, but I have one more question. So we're
Please.
sending a lot of spacecraft right now on the moon. Firefly just published a beautiful video. I don't know if you saw that yesterday or 2 days ago, of the spacecraft flying above the moon with super high quality. I think it's 4K image, right? So yeah, have you been contacted by those companies, iSpace, Firefly? I don't want to Intuitive Machine or any, so you can implement this software on board the orbiters?
Someone contacted us, so not the ones that you mentioned, but we are in contact. We are actually also thinking about using. That's why I'm showing in the background. We are also thinking maybe to look into some commercialization of this algorithm or similar algorithms too, because someone needs to prospect the moon if other people want to start making business there. So there's certainly also commercial applications of these things that we are developing right now. Yeah.
Okay. Chris Fele asked about something that people always ask, so I'm gonna I want these questions to be: is there any evidence of remote sensing data of obfuscation? So, did you see in your data that the data set you had access to, that there was some data which were voluntarily removed by someone?
So I don't think so, at least not so far. I'm not sure if did you find anything, Adam, or were there any outliers that looked like they were tampered with or something? I
No,
don't think
maybe
so.
just the stuff that we accidentally deleted.
Okay.
That's a joke.
Yeah.
There is interesting data artifacts in the LRO where the side, some of the images that we get, there's like a black band on both sides, and that's just our artifact of the instrument. And for some time, that was a bit messing up our algorithm. We were able to get around this, but that was more of an instrument artifact where kind of the side it just doesn't have like sensors on it. So
We're almost at the end of the half hour, so I just want to clarify. So these data, the data you use, are publicly available, right?
The
So
data
everybody can
as
download
well
it.
as our code, yeah. So people can download our code and download the data and run them in the cloud and see, search for themselves. I mean, they need a pretty good computer to do that themselves, but in principle, all the tools are out there, the data is out there. So, and we would be happy to actually have other people, trying the same, confirming our things, looking at other patches of the moon. So, yeah.
Okay.
yeah, the images themselves, they're on the ASU, Arizona State University, other places servers. So that's like the data for the LRO, and then our code is on GitHub. Data labels are on GitHub. Model weights, there's a link from our GitHub page on it. So go wild, please.
Okay, good. So if you're interested in this type of research, or you're skeptical about it and so on, you can do it yourself and check by yourself the result of this algorithm and testing it on different type of observation as well. Adam, so what's the next step for you? You published this paper last year. Now you're in UC Berkeley. What are you doing?
That's right. Yeah, I'm working on basically AIs, large language models in particular, and trying to make them aligned to human values. And there's a lot of questions there. How do you take these large language models, these kind of artificial intelligence that we're building, and make them care about the things that we as humans care about? So there's a lot of technical questions. So there's like the current framework or the paradigm that's used in the industry, this like reinforcement learning from human feedback, RLHF. And then there's potential failure cases of that. So these things that we're building that are getting increasingly more intelligent, how do we make them aligned and care about the things that we as humans care about, so that we can have safe, reliable, useful, increasingly advanced artificial intelligence?
Good. What about you, Daniel? What about this project? What's the next step?
Yeah.
You alluded it,
Yes.
so
Yeah. So for this project, we actually won a small or one of the master students working for us. So Cameron, shout out to him right now. He won a proposal from the SETI Institute actually last year. So we are currently still in the process of delegating that money, but this is going to be used to do this global scan. So his PhD thesis is going to be using these funds, that one proposal, to do the whole the global lunar scan, and then also already start thinking about what the next data sets could be. So what would be the most logical step going for Mars data, probably that exists, check what other data there's lying around in the NASA archives and ESA archives that we could deploy this algorithm to. So that's the next step. So stay tuned. Maybe by end of the year we have the global map and maybe even the crashed UFO. Let's see.
okay, that would be great. Go ahead.
I should add very quickly, everything we said is nothing really specific about lunar image data set. So one feature of this algorithm is that it's data set agnostic. So it could be images of Mars, it could be images wherever you have surface imagery, but also like electromagnetic EM radiation imagery, spectrographs from that, other sorts of data. So this is kind of a data format agnostic approach, that if you have a data set that you want to find anomalies, test light curves, other things, I would encourage you to try it and see what you find.
All right. Well, thank you very much. Then that was your final thought, I'm assuming. I just want to say thank you to all of our viewers. Thank you for your patience, and I hope we answered to some of your questions today. Thanks, Daniel, again for being a great participant to our City Live. We see you another time, hopefully.
Yes,
My
always,
microphone is hanging.
always.
Can you hear me? Because my microphone is dying.
Yes,
So
yes.
it's good? Aye.
You can hear
It's
you.
not my audio. Not good with my audio. Adam, I see you at UC Berkeley or at SETI Institute in the future. Nearby?
Yes, if you're around, let me know.
Okay. And yeah, so people, you can have a look at the paper, you can have a look at the database, the code, and do everything by yourself. And join the SETI Institute as an affiliate or volunteer to help us in discovering artifacts on the moon or elsewhere. So thanks again. You can support the SETI Institute by going to our website at seti.org. If you incline and you want to help Daniel to run his massive supercomputer network, you can also make a small donation. There is a button somewhere called donate or something like this. And you can even write in the text, I'm making this donation on behalf of Daniel for helping him running this massive algorithm. Okay? And yeah, we see you next week. I don't know what will be the show next week, but Bess will be probably the one moderating it. And it will be fun as usual. So thanks, and see you on another planet.
Excellent. Thank you all.
Bye-bye.
Take care.